I'll be covering convolutional neural networks today. This is just starting with the basics. And we did plan to cover a tutorial after the slides, but if we don't have time, we can do it next time, or we can share the tutorial notebook. Feel free to interrupt me if you have any questions, and I'm going to try to go slow. Okay, so first of all, what's the motivation for convolutional neural networks, right? One of the motivations is that with these fully connected networks, when we're building these deep nets, they are huge and there are lots of parameters that we are training. And so the question is, can we build a smaller network that can help us achieve the same purpose? So we know it's good to learn a small model because it's computationally efficient. And the question then arises, given this fully connected model, do we really need all the edges in this model shown here? Can we get rid of all the edges and still have the network perform the task that we want to train the network on? For instance, a simple classification task, right? And the other question is, okay, even if we don't need all of the edges in this network, can we actually share some of the weights on some of these edges in the network across the different neurons? So those are the questions that inspired the convolutional neural networks. So we can notice that if we're given a particular image, then there are certain patterns in the image that are much smaller than the image itself. And here I'm showing, for instance, the beak of this bird. And so we can imagine implementing something like a small beak detector, which instead of detecting everything in this image, just focuses on detecting beaks, right? So yeah, we can call this a beak detector. It's just taking the small part of the image, passing it through summing all the activations and passing it through a nonlinearity, and that gives us a beak detector. And so what it helps us do is it helps us represent a small region in this entire image with fewer parameters. So the next question is, okay, what about training a lot of such small detectors, right? Now I have two different images. Both of them have birds with beaks. And I could potentially implement one beak detector, which detects the beak on the upper left corner of the image. And I could implement a beak detector that detects this beak in the middle of the image. And what we want to do with convolutional neural nets is to compress these such that they can use the same parameters. So my goal is to just have one beak detector such that it will just detect the beaks in different parts of the images. And that can be done by sharing the weights that are that this beak detector is being trained on. So this was kind of the motivation for convolution nets, and this is a basic diagram showing what a convolutional operator is. So a convolutional neural net is a neural network with some convolutional layers, and usually there are multiple of them. And it has a number of filters. So in these networks, we call weights as filters. So these are some m by n matrices. And so you can think of this filter as analogous to the beak detector. So you can imagine that if this was your beak detector, then if you kind of scan this beak detector throughout this image, then it will help you detect the regions of the image which contain beaks. So next, I'm going to kind of walk over what the convolutional operation itself looks like. So here, this filter is being convolved with this input image to produce some output. And we'll see how it actually does that. How does that operation work? So consider this to be our input image. It's a 6x6 image, which is just represented in this form by zeros and ones. And we can consider two different filters uh, given by these two matrices. And so when I say filters, these are the parameters which we actually want to learn, right? And we initialize them with certain numbers, and then try to learn them through back propagation. And so here, what we're doing is, since each filter is 3 by 3, each filter, what intuitively is doing is basically detecting a small pattern of this image, which is 3 by 3. So you can see there's this pattern being detected, and I'll show you how it's being detected. So let's just look at the first filter, right? And let's just see how can we do convolution using this filter and the input image. So what we do is we basically compute the element-wise multiplication of each of the elements in the filter and a corresponding region in the input image, and then just sum them up, and that gives us one number, right? So we can view this as a dot product of this filter with this region of the image, which is of the same size as the filter. And so that gives me one number. So you can see that this full region has been converted to just one number instead of a 3 by 3 matrix. And if I consider, so there's this parameter which we can set in a CNN, which is called stride, which determines how I'm going to move this filter across this image. So if my stride is 1, that means I will just move the filter by skipping one column, right? So you can see if I just move it by one column, then this would be stride 1. If on the other hand, my stride is 2, okay, so this is just showing the result of convolving this portion of the image with the filter. And that gives us another number. Now, if my stride was 2, then I would take this convolution and that would give me the first number. And then I would move this by 2 columns and that would actually give me the second number. Right, so that's the concept of stride. It's a parameter which you can tune, which lets you decide how you want to convolve this filter with the image, and how do you want to, by what number of steps do you want to shift the filter as you're convolving. So going back to the stride 1 case, this is how it's going to work. So you have a 3 by 3 filter, you convolve it with 3 by 3 region of the image and you get one output. Then you move it, and then you do the convolution operation again, and that gives you another output. And then you move it again, and that gives you another output, right? So you're just doing dot products of these regions with this filter. And then again, and now you move it to the next. Again, because my stride was 1, I just shift the filter by 1 row rather than more rows. And so we repeat this process until we reach the end. And so you can see that what has happened is that we had a 6 by 6 input image and we had a 3 by 3 filter. And what we've done is by convolving this filter with this image, we've reduced the 6 by 6 image to a 4 by 4 image. So does anyone have questions up till now? Okay. In that case, I'll keep going. So now we can think of, okay, so now we can look at what pattern, this is kind of showing what pattern this filter is encoding. And you can see that if I look at this pattern in the filter, you can see that these patterns are seen in these two regions in the image as well. And correspondingly, you see higher values at the outputs, which are detecting that these patterns exist in these regions of the image. So that's kind of like how this filter has, and the convolution operator has helped detect those patterns which were occurring in the original input image. And so now we come to the second filter which we had, and we repeat the same process. So in this case, what we do is we again convolve this filter with the first region of the image, and that gives us one output unit. And then we drag it, and that gives us second output unit. And we repeat the process, right? And in this case, again, because the stride is fixed to 1, we get another 4x4 image, right? So these are two filters which are detecting different patterns. And what this forms is a feature map. So you can think of the first filter giving us um, an output image which is detected first set of patterns. Let's say that it's detecting beaks, and the second filter has given a second set of 4x4 image in which that filter is detecting, let's say, claws, right? So the feature map consists of both of these images. So in this case, the depth of the feature map is 2, and each of the images in the feature map itself is 4x4. So it eventually basically forms a 2x4x4 matrix. And so so far the input image was just a square matrix, so it didn't have any depth. What if our image is actually a colored image rather than a grayscale image? In that case, what happens is that we have the 3 different channels corresponding to the red, green, and blue parts of the images. And so then our image, instead of being an m by n dimensional image, is actually 3 by m by n dimensional. So that's going to be our input image. And our filters also correspondingly will be 3-dimensional, right? So we can see that our input now has a depth of 3 instead of 1, and our filters also have a depth of 3 instead of 1. And in this case, each filter in this, in this first given filter, each of these matrices is called a channel, right? So the depth of your filters determines the number of channels you have in the image. So it's just a terminology thing, but these are usually called channels. So that's how we can generalize from grayscale images to colored images. And so this takes us to comparison between convolution and fully connected nets. So you can see that in a fully connected net, you take the input image, and usually you just flatten the input image. And then you have fully connected weights connecting each unit in the input layer to each unit in the hidden layer. But in the convolutional nets, you have these filters, and these are your weights. And these filters are actually shared between different parts of the input. And so these are shared weights, and they give you these feature maps as outputs. So let me just make this a little bit more clear. So going back to the first filter, we can see that when we convolved this filter with the first region of the image, we got the first activation in the output image. And if we look at how this would look like analogous to a fully connected net, then we have this flattened version of this image here, and this output activation in the next layer. And these colors are going to show how the weights from this input layer are connected to this output layer. And so one thing to note is that you only connect to 9 inputs, right? This output is only connecting to 9 inputs instead of connecting to all the inputs. You see that there are some inputs which do not have connections to this output node. So the first thing to note is that we have reduced the number of edges as compared to a fully connected net. So which means we have fewer parameters. Then the second thing to note is that when we move this filter, then and we have another output unit. If we plot these weights again, then we see that we are actually using the same weights, right? So these colors are just showing the weights, and you see that these set of weights are actually the same as these set of weights. So that means now we have shared weights. So we have fewer parameters because we've reduced the number of edges, but also because now we are sharing the weights from the input layer to the output layer. So which means even sharing the weights implies even fewer parameters. So that's one of the big advantages of using a CNN, that you really reduce the number of parameters as compared to a fully connected deep network. So this is what the whole CNN pipeline looks like. So basically you have, let's say, an input image of a cat, And let's say your job is to classify whether this image belongs to, for instance, a cat category or a dog category, and so on. And so usually a convolutional neural net would look like this. You'll have an input image, you'll have a convolutional layer, and then you'll have this max pooling layer, which we haven't talked about, but I will explain what this is. And usually you would have multiple of these convolution and pooling layers. And in the end, you usually flatten the network and pass it through a few fully connected layers, usually just two fully connected layers. And I'll also explain how this flattening is done in the next few slides. So the first question is, what is pooling, right? And why are we doing pooling? So pooling really is just subsampling of your input image. So you can imagine that, or you can see that basically, given this image, if we just subsample this image to form a smaller image, we haven't really lost much, right? We can still um, figure out what the image is, all its features, and there's nothing lost in terms of, there's not much lost in terms of the information. And so we can subsample the pixels to make the image smaller. And why do we do that? Because again, it helps us reduce the number of parameters which we need to characterize the image. If we have a smaller image, then we'll need less number of parameters to further characterize this image. And so this is the concept of pooling. And so there are multiple ways of doing pooling. And one of the most common ways of pooling is called max pooling. And let's see how that works. So again, we have our, okay, so remember we had this filter and we had an input image, and convolving this filter with the input image gave us this 4x4 output image. And so how do we, and then we also had a second filter, and that also had a corresponding 4x4 image. And now our goal is to apply pooling to this, to both of these output images. So the way we do that is by defining the size of the output units on which we want to do the pooling operation. So in this case, we've chosen the size to be 2x2, right? So we want to do the pooling operation for each 2x2 part of the output image. And by max pooling, what we mean is that for each of these regions, which we've defined in the output image, we just select the maximum, maximally activated neuron, right? So in this case, this is the maximal activation. So we just select this. And similarly, here we just select 0. Here, the maximum activation is 3. So we select 3. And here it's 1. So we select 1. And so on for the second filter as well, right? So what we've done here is we had a 4x4 output image, and we have actually just reduced that to a 2x2. And similarly here, the 4x4 output image corresponding to filter 2 has also been reduced to a 2x2 image, right? So in a sense, we took an input image, which was 6x6, we performed convolution, and this gave us 4x4 images corresponding to each of the filters. And then when we apply max pooling, we further reduce the size of those images to just 2x2 images, right? And we have two sets of 2x2 because we had two filters. So that's what the max pooling operation is. So yes, so the new image is just smaller than what we had from convolution. And till now, I just want to summarize that we've seen that CNN is compressing a fully connected networks in two ways. One, it's reducing the number of connections. Two, it uses shared weights on the edges, which in turn reduces the number of parameters. And then three, it's using max pooling, which is reducing the complexity even further. And it also leads to translation invariance, because when you are taking a region of the image and you're just taking the max of the activation, this means that small changes in the activations of the units wouldn't make much difference in the processing of the network. So that leads to this property called translation invariance, which means that even if your input images were slightly perturbed, you would still get good results. And so going back to a pipeline, basically we have this set of convolution and pooling layers in the CNN, which can repeat many times. So at the output of the first pooling operation, we get a new image, which is much smaller than the original input image. Then we pass this new image to another set of convolution and pooling layers. And that gives us another new image. And then we take this new image and flatten it and pass it through a fully connected network. So now now that we've seen convolution layers and pooling layers, I'm going to explain what this flattening is and how that is going to operate.
Sugandha, let me just make a quick point to remind the students of what we saw in terms of mammalian visual neurophysiology. So the filters that Sugandha talked about are analogous to the receptive fields that we saw, say, at the level of the retina or the lateral geniculate nucleus or the primary visual cortex. So these receptive fields don't have access to the entire, yep, so Sugandha has that there, don't have access to the entire visual field, but rather they're looking at small sections of the visual field. And the same kinds of computations are being done across the entire visual field. The brain is trying to detect whether, say, there's a rightward diagonal in every little section of the visual field, kind of like weight sharing that Sugandha talked about. The other notion that Sugandha brought up of max pooling, that is reminiscent of the relationship between simple cells in V1 and complex cells in V1. So you remember we had talked about simple and complex cells in the primary visual cortex, both being tuned to, say, particular orientations. But the difference between a complex cell and a simple cell is that a complex cell doesn't really care exactly where that oriented bar appears in its receptive field. Whereas a simple cell is very tied not only to the orientation, but also the precise location of the bar. So a complex cell can be thought of as arising from the max pooling applied across multiple simple cells, and thereby the complex cell gains a level of translation invariance. So these ideas in the convolutional and the max pooling layers of deep networks are very analogous to the kinds of known physiology in the mammalian visual cortex. Okay, Sugandha, back to you.
Yeah, so on the same note, right? And I think this was mentioned in the last class by Pawan also, that even in these filters, if we try to visualize the filters, the kind of activations we see are very similar to the kind of edge detectors which these simple cells are implementing. So what we see is that if you look at the filters in the earlier layers, so we talked about having multiple layers of convolution and pooling layers. So if you look at the filters in initial layers, we see that the filters are implementing something like these edge detectors. And as we move to intermediate layers, we see that they start recognizing some simple shapes. So in this case, this network was trained on faces. So initially, earlier layers detect edges, but then intermediate layers are detecting shapes like you can see noses and eyes and things like that. And then further, even the deeper layers end up detecting higher level features, just such as like the whole facial shapes. So in the sense that Pawan was saying, it's very similar to what we see in the human brain, where we have simple cells that kind of act as edge detectors, and then we have complex cells that arise out of the max pooling operations on these simple cells. Okay, so going back to how we are doing flattening at the end of the network. So this is the output image. So let's say this output image at the end of our convolution and pooling layers is this 2x2 by 2 matrix, right? So we have this feature map as the output. And so how does flattening work? We just flatten these into one long vector. And then we basically pass this long vector through a bunch of fully connected layers. And usually we just use 2 fully connected layers. So on the whole, this is the pipeline, right? And I'm going to now explain this in the context of using this in keras, since that's what we're using in TensorFlow. So you have the input and you perform convolution. So usually you would use something like model.add convolution 2D, and you specify these parameters. So what this means is that this 25 by 3 by 3 means that there are 25 3 by 3 filters which we want to train, and the input shape is 28 by 8, right? And this 28 by 28 means the 28 by 28 pixels in the image, and this last dimension 1 corresponds to whether the image is black and white or whether it's RGB color, right? If this is 1, then the image is black and white. If this is 3, then it's a colored image. And then you apply max pooling by adding a max pooling layer. And here you've specified the region over which, the dimensions of the region on which you want to apply max pooling operation, which here is 2 by 2. So you just take every 2 by 2 region in the output and apply max pooling on it. And so we can imagine that if given 1 by 28 by 28 input, we pass it through the convolutional layer. In this case, the output is going to be 25 by 26 by 26. And this is because we are convolving a 28 by 28 image by 3 by 3 filters, right? And that reduces each of these to 26 by 26. And we have 25 of them because we have 25 filters. So we have 25 feature maps. And then we apply max pooling. And that means because we are applying max pooling on a region of 22 by 2, this reduces this each of these 26 by 26 images to 13 by 13 dimensions. And then we can further apply convolution again. And this time we're using 50 filters of dimensions 3 by 3. So that reduces our images to 11 by 11. But because we are using 50 filters, so we have the depth is 50. And then we again apply max pooling, and that further reduces these 11 by 11 images to 5 by 5. And so the question is, how many parameters do we have for each filter in the first layer? Because we had 3 by 3 filters, so the total number of parameters in the filters in first layer is 9. And that's per filter. And since we have 25 filters, it's actually 25 times 9. And similarly, how many parameters do we have for each filter in the second layer? That's going to be 25 times 9, which is 225. So that's kind of the basic chain. And after we have this output image of 50 by 5 by 5, what we do is we just flatten this, right? And on flattening, we can use this additional layer to flatten this output image in keras. And flattening gives us a vector of 1,250 dimensions. And then we just pass it through a fully connected feed-forward network. And we know how to construct this from the previous tutorial. So here we are just going to add a dense layer and the corresponding activation, and then another dense layer and a softmax activation, because if we are doing classification, right? So in this case, we just add 2 fully connected layers at the end, and that's it. So that's basically all I wanted to cover.